Hello everyone, I'm Zekai Shao, a PhD student from Fudan University and a member of VIS under the supervision of Professor Chen. Today I'm here to present our work VQA or VECA on the topic of explainable AI for open domain question answering tasks through visualization and visual analytics. Our team comprises researchers from VIS, Fudan NLP Research Group, and the University of Warwick. In this talk, I'll cover the background in NLP, the framework, and the details of VECA, a combined evaluation using case studies and the expert feedback and the insights we've gained from this project. Firstly, open domain question answering or OpenQA is an essential task with broad applications in everyday life. When you search for a question on a search engine such as where is the coldest place in the world, modern search engines not only list the most relevant websites entries, but may also directly provide you with a predicted answer, such as East Antarctic Plateau. This answer is extracted from a piece of text. Of course, we can now also directly ask ChatGPT, which will generate more detailed responses. Our focus is on the former kind of OpenQA, which employs BERT-based models for extracting answers from text. Besides, the challenge lies in explaining such models. The complete task of extractive OpenQA generally involves two steps, retrieval and reading. The DPR model on the right is an example, with a retriever consisting of two encoders and a reader with both a selection head and an answer head. Explaining such multi-module complex models is a huge challenge. The second challenge comes from large-scale datasets containing long passages. The original corpus, such as Wikipedia, may contain at least tens of millions of passages, and each of which has at least as many tokens as the text shown in this figure. A retriever then selects the top K documents from this, where K could range from 10 to 100. Understanding the model's decision-making process over this vast amount of lengthy text is difficult. And the third is the gap between understanding individual parameters and the overall decision-making process. Recognizing the importance and challenges, we propose VECA to address this issue. First, we discussed with several NLP experts to identify multiple analysis tasks. The first one is understanding what happens within individual models of the model. And the second is comparing the mechanism and decision differences between different modules. And the third is understanding why passages other than the automated selected one among the top K passages were not chosen. And the last is linking the decision-making process to the type of task. We realize that the first step in this process is to extract key information and abstract interpretive data at various levels to disentangle them from complex data and parameters. Therefore, we use feature attribution algorithm to extract keywords in each module based on the saliency score, and use their attribution algorithm to take the aggregation of attention gradients as the response of the layer to identify key layers. In addition, we extract token pairs with high attention attribution scores and use greedy algorithm to generate semantic trees from the top layer to the bottom layer to avoid having the user look at large attention metrics or other chaotic attention interpretive resource every time. So the workflow of VECA is to feed the inference data from the OpenQA model into the aforementioned explanation engine and to put in the resource into different views for display. Use interaction changes the filtering scope of the data transmissions. Our interface consists of one user panel and 4 views. The user panel provides statistical information about the model and dataset as well as color legends. The summary view presents a global summary of performance and the model responses for subsets with a Sankey-based diagram. The context view presents questions of selected subset and the context of passages retrieved for a selected question, which complement the instance view. The instance view summarizes the focused words of each candidate passage in different modules of the model and their different distributions with ranking visualization incorporating text. And the tree view explains the local data flow within a single module or multiple modules in the pipeline with comparable Sankey tree layout. When it first comes to our tree view visualization, we've carefully considered the characteristics of generated trees for an intuitive design. The source and the importance of attention are encoded through varying edge colors and widths. Similarly, the origin and the importance of words are represented through node colors and sizes. We offer two modes in tree view, one for comparing semantic trees across different modules, and another for tracking the evolution of trees within a single module. This dual mode approach facilitates a cross-module decision comparison and provides insights into the decision-making process within individual models. To demonstrate the effectiveness of VIS, we showcase 3 case studies, ranging from introductory to advanced. Today I'll focus on the later 2. First, we have a case where VIS helps in distinguishing a successful decision-making process. And second, we delve into how VIS can be used to understand the reasons behind the performance improvements brought by new training methods in retrieval tasks. Experts use VEQA to explore DPR with natural question dataset and try to categorize a successful case of decision. In the summary view, the expert found a potential relation between model response and the performances for success. Specifically, by looking at the grouped bar charts, experts found that who played and who plays were the 2 groups with relatively poor top K accuracy but better EM. And the corresponding response of force layer for re-ranker was significantly higher than the other classes. So they clicked the link in Sankey diagram and jumped to instance table in context view to discover whether it was the force layer of re-ranker that made the system do the correct prediction. After that, experts clicked on the row where who played in the first shades of gray was located to explore this instance in detail. In the instance view, experts found that candidate 3 containing the golden answer moved from 3rd to 1st place after re-ranking, while candidate 2 that was in 2nd place after retrieval dropped to 7th. So they looked at the bar chart above the first column, lowered the silences threshold, and found that gray was considered an important indicator by question encoder and was a part of the title in candidate 2. So they suspected that candidate 2 was ranked high because of gray, and they further dived into context view and found it was an irrelevant passage. Moreover, they clicked the third row, to know the context of candidate 3. Although the title of candidate 3 was 50 Shades of Grey Film, which overlapped greatly with the question. The highest scoring word was film except for the SEP. Experts argue that retriever noticed the place in given question, that is, the target of passages to be searched for was a movie rather than a novel, which illustrated a superiority of dense retriever over traditional methods that rely on keyword matching. Now experts wanted to understand how re-ranker found the difference between 2 candidates and modify their order. Looking at the re-ranker tree for candidate 2 in tree view, they found that the most obvious change in the force layer was the addition of all the grades in the passage and the critics for the identity into the tree structure. Expert believes that re-ranker confirmed here that candidate 2 was irrelevant. Then experts view re-ranker tree of candidate 3 for comparison. The most significant change at the same position for candidate 3 is the addition of another small part of the answer, RMA, and the film in the title into the tree structure. Experts believe that re-ranker had already determined the possible answers here and used this as a basis for re-ranking. Additionally, by clicking on the drop-down bar and comparing it with the reader tree at a layer level, they found that the structures and the evolutions of 2 trees for candidate 3 were similar. That is, rather correlated the possible answers and questions at higher layer to determine the prediction. Next, we employ Veka to explore why the DPR2 released on GitHub trained with more sophisticated negative sampling methods outperform its predecessor, DPR1. Our examine starts with a quantitative observation. Experts noted that in DPR2, the yellow bars representing performance metrics for all categories are almost uniformly distributed around the mean, suggesting balanced retrieval performance across the board. And furthermore, they observed that both encoder in DPR2 retriever exhibit stronger activations in higher layers compared to those in DPR1. With this high-level overview from the summary view, the experts aim to delve deeper into the root causes of the improved performance via a detailed view. By examining a specific example where DPR2 succeeds in extraction but DPR1 fails, the experts found a lowered focus on the pink-colored title words might be a contribution factor. Additional quantitative analysis confirmed a significant reduction in the proportion of title words within varying filtering scopes, thus validating these key insights. In our interviews with experts, we've gained several important insights. One key takeaway is the need to balance quantitative analysis with visual insights. While statistical metrics lend credibility to visual observations, the experts often express their comprehensive visual insights give them intuitive confidence in their understanding of the decision-making process. Therefore, both are indispensable. Another critical aspect is the integration of Veka into a developer's environment. We believe a reliable approach to this is to first understanding the work environment of the experts, which is often Python, and identify the visualization tools they are almost comfortable with, such as TensorBoard. Plugging developed on top of these familiar tools is likely to facilitate better integration. And we've also encountered skepticism around the very interpretability of attention mechanism. In this regard, we believe the key is to focus methods trusted by the experts and cater to those who already value their approaches. To ensure mutual understanding and iterative development, finally, we've discussed the generalizability of Veka, a crucial aspect that underlines its value. Due to the time limits, we skipped the other three discussion topics. We claim that Veka is a highly generalizable system. It is designed to be compatible with transformer-based OpenQA models, irrespective of whether they are extractive or generative in nature. This also encompasses various subtasks within the broader field of QA. However, it is important to clarify that Veka isn't directly applicable to QA systems that are based on knowledge graphs or those that utilize reinforced learning or graph neural networks. As we navigate through the area of large language models, the burgeoning capability of these models, along with their exponentially growing parameter counts, will undoubtedly introduce new opportunities and challenges in the field of explainable AI, and we believe that Veka serves as an important stepping stone in this evolving landscape. Thank you for your listening, and please feel free to visit our group's website at FDU VIS from Fudan University.